this. All right, let's get started soon. If everyone wants to take their seats. All right, let's get started. The final session today. So I'm Kate Rowlands. I'm an astronomer here at Space Telescope, and I'll be your chair. Yanze Lo will be moderating online, and Kalina Nekova will be running the mic. So this is a continuation of kind of our CGM and feedback session. So now we have Floriane Leclerc, and she will talk about preparing for JWST to unveil the sources of cosmic reionization.
Thank you. Can you hear me? Yeah. Yeah, good afternoon, everybody. So I'm Florian. I'm a postdoc at UT Austin. And today I will be presenting some work that have been carried out within the LZ-LCS collaboration, and which aims at mapping the gas around local star-forming galaxies that also have been confirmed to be Lyman continuum leakers and non-leakers. And the main goal of this analysis is to understand how Lyman continuum photons escape those galaxies and what makes those galaxies Lyman continuum leakers, and ultimately to understand the sources of cosmic reionization. So I know that is not the main focus of this conference, so I'll start with a brief introduction. And so cosmic reionization, briefly, it's one of the last changes of the universe, and that's actually the only one initiated by the galaxies themselves. And we approximately know observationally when it ended. I mean, it's when the first galaxies of the universe produced enough ionizing photons to be able to ionize the gas between the galaxies. And so observationally, we know when it ended, but we don't really know how it happens. And so the two main candidates, let's say, for the sources of cosmic reionization are the accreting black holes or the massive stars in galaxies. Question is, which kind of galaxies? Low mass, high mass? So thanks to JWST, we are now getting more and more observations of galaxies within this epoch. And we also get exquisite details about those galaxies, and what we know from those observations is that they are emitting tremendous amounts of ionizing photons, and this is illustrated by the recent work by Akimatek 2024, where we see that high-redshift galaxies indeed have ionizing photon production efficiency very high, and actually higher than the canonical values at those epochs. But the main question, the important point here for cosmic ionization is how much of the Lyman continuum radiation actually escape those galaxies, right? And so Lyman continuum photons can be absorbed by neutral gas and dust. And this is illustrated by a simulation work by Mauhofer 2021, where you see, so it's a comparison between the intrinsic Lyman continuum map on the left and the actually observed Lyman continuum map. So, and you see that the Lyman continuum emission is dimmed, so it's clearly fainter. And so that's this quantity, so how much of the fraction, how much of the escape fraction of Lyman continuum photons. This is what we would like ideally to measure at the epoch of cosmic ionization. But as you might know, it's impossible to observe Lyman continuum photons at those epochs because the neutral hydrogen, the IgM, is still mostly neutral. Okay, so we need to basically find indirect tracers of those Lyman continuum photons at lower redshifts. And those tracers need to be tested and calibrated on lower redshift galaxies where Lyman continuum is indeed observable. Okay. And so even at low redshift, observing Lyman continuum emission is quite complicated. And like the first detections were reported almost 10 years ago, so quite new. And just to give you an idea, in 2021, only 20 low redshift Lyman continuum emitters were known. And those are the well-known green peas, so compact ionized Lyman alpha emitters. And this is only a few years ago, thanks to the LCL survey, and thanks to Sophia, we had a nice overview right before the break. And so this survey is actually a large program, cost large program, which is targeting 66 star-forming galaxies at redshift 0.3, so local galaxies. And those galaxies have been selected to be likely analogs of high-redshift galaxies, and also to span large range of different properties. So in O3 to ratio, UV slope, different concentrated star formation, and also include some previous detection from the literature. And so with this, we have, for the first time, a statistical sample of Lyman continuum leakers and non-leakers to be able to really test and calibrate indirect Lyman continuum tracers, but also to understand how Lyman continuum photons escape such galaxies. And so this is the work I want to present today, is basically trying to connect the Lyman continuum escape to the gas distribution. And to do that, we made some follow-up observations with the IFUs, so KCWI and LRS2 at HET in Texas, of a subsample of the LZLCS galaxies, and also some galaxies from the Isotov et al. 2022. And those 22 objects are both leakers and non-leakers. And this work is aiming at really understanding how the gas in ISM CGM impacts the escape of ionizing photons in those leakers. And so this is a recently accepted work on arXiv. And so in order to characterize the gas distribution, what we have done is basically to use magnesium-2 as a tracer of the neutral and low ionization gas, and O2 as a tracer of the ionized gas. And from those maps, we determined the spatial extent of the gas, and also the spatial offsets between the bulk of the gas and the stars, basically, the continuum, UV continuum of those galaxies. And the goal is really to connect those spatial nebular properties with the known properties from the LZLCL survey, and especially this Lyman continuum escape fraction. Okay, so how did we characterize the spatial extent of the nebular emission? So here I'm showing an example of a magnesium 2 map, and basically, in order to measure the extent, we just fitted like a 2D exponential model, and this is the surface brightness profile here, and you can see the magnesium 2 profile in purple, and you can see that it's significantly like more extended than the continuum, so stellar content, which is shown in black. And so in this case, we do detect like neutral or low ionization gas around these objects. We did the same for O2. And in this case, we have, so the O2 and continuum profiles are following each other pretty well. So compact configuration, no extended ionized gas around these objects. And so we did that for the 22 galaxies. And if we compare, for instance, the extent of the magnesium 2, so neutral, low ionization gas, compared to the stellar content, stellar size, so UV continuum, we see that we have 7 objects which are above this one-to-one relation, meaning that we detected significant extended emission in magnesium 2 for all of them. And I'm not showing the results for the O2, but we also detect O2 halos around 10 objects of the sample. And which is interesting here is that magnesium 2 halos, when both magnesium 2 and O2 are more extended than the continuum, magnesium 2 is always more extended by a small factor, 1.3, but still more extended than the ionized phase. And also, the nebular emission is more extended by a factor 1.5 than the continuum, but this is certainly a lower limit, as they might have some sensitivity limitation here. Okay, we did the same. I mean, we also looked at the spatial offset, as I was telling, between the continuum, the cross, the plus, and the bulk of the neutral gas here, and the ionized gas. And we detect not show any offsets between the two, but we observe like large offsets for some objects, 4 kiloparsec offsets, and smaller offsets for O2, for the ionized gas. Okay, and if we compare these offsets compared to the size of the galaxy, we do kind of see a weak correlation for magnesium 2, but not for O2, and we'll discuss that a bit later. So now that we characterized the spatial distribution of those galaxies, let's connect those properties to the Lyman continuum escape. And this is what I'm doing here. So this is the Lyman continuum escape fraction as a function of the size, magnesium 2, so neutral and low ionization gas. And so what we see is that the strong leakers, so escape fraction higher than 30%, are all compact or even unresolved in our data, compared to the weaker leakers. I'm just highlighting this one, which is also a strong leaker, but with extended neutral gas around it. I'll come back to this later. And but we also, for the weaker leakers and non-leakers, we see a wide diversity, right? With some unresolved objects, very compact, and some very extended objects, objects with extended magnesium 2 halos around them. Okay. And so basically, if we want to select our main results, is that if we are looking for Lyman continuum leakers, we need to be like compact in the nebular configuration and also highly ionized. So those points are color-coded by the O3-2 ratio, and you see that those objects are all have high O3-2 ratios. Okay, the kind of same results for the spatial offsets, where strong leakers do not show significant spatial offsets between the stars and the gas. And so in order to confirm those individual trends, we did some stacking experiments. So what you can see is different stacks. So the continuum, magnesium 2, so neutral, low ionization gas, and more ionized gas with O2. And while the continuum, and so the first row is the strong leakers, the middle row is the weak non-leakers, and you can see that the continuum, the continuum size are not so different for the weak and strong leakers, but the nebular configuration is more extended for the weak and non-leakers. quickly I'm comparing, so I'm showing the surface brightness profiles of the stacks for the strong liquors. So all profiles are following each other quite well. So liquors are compact. And if we look at, the weaker liquors, here we do see an interesting behavior where the O2 is more extended than the continuum, but magnesium 2 is also more extended, but even more extended than O2. And this is maybe, a sign, an indication for magnesium 2 resonance scattering in those objects. Okay. Quickly, we looked at what drives this nebular compactness in those objects, and we found that the size of the nebular emission depends mostly on being highly ionized, basically. So highly ionized means compact configuration. We also checked, we did not find any correlation with, for instance, the SFR surface density or other properties like stellar mass or even Lyman alpha properties. And so we discussed different mechanisms for the Lyman continuum escape. For the highly ionized galaxies, we might be in this configuration where we have a widespread ionization allowing Lyman continuum photons to escape. Maybe because we do detect neutral gas, we are in this configuration where we have numerous porous line of sight. And finally, for the low ionized galaxy, like this one, if you remember, the strong liquor with halos, with the magnesium 2 halo, we might be in this scenario where Lyman continuum photons are escaping through channels which have been cleared by flows. And I'm almost done. I'm done. Yeah, I just let you with my conclusion, just maybe a teaser, because in my abstract I said that I will show you some kinematic maps, and I'm still working on them, but I'm happy to discuss with you if you want more information about them. Thank you.
All right, what are your questions? So I'd like to prioritize junior folks in the audience especially. So I will leave a few seconds for people to ponder their questions, raise their hands. It's an awkward pause, it's okay. Questions? Okay, Amrata.
Really nice talk. So I was wondering, since you talked about the effect of outflows on like the liquors, so I'm wondering if you have found any trends in the kinematics of the O2 in the liquors versus non-liquors.
Yeah, so I'm actually working on that. Okay. And so no, we did not find any. So we found rotation. So those objects are rotating. We also find rotation velocity gradients in MG2, and we do not find any correlation with Lyman continuum escape. So. No.
More questions. You can also ask questions online as well, highly encouraged.
But it's preliminary work.
Have you been able to see if there's any azimuthal trends? Because it seems like maybe some of those scenarios predict kind of an isotropic trend, but some you might see trends in specific angles and not in other angles.
Yeah, so it's also work in progress. So we do not really see any trend right now, but those galaxies are very compact, so it's also hard, to find the rotation. I mean the angle, inclination angle, right? Maybe if I can just show one of them.
So you need an optical UV IFU in space.
Yay! Would be awesome. Yeah, they are very compact, so hard to know.
All right. One final question whilst the next speaker comes to set up.
Hi, I was just wondering about the spatial offset that you have there. If you do see a spatial offset between the magnesium 2 and the ionized continuum, is that primarily due to the outflows that are happening, or I'm just wondering what your intuition, if you could share some intuition on
a spatial offset between magnesium 2 emission and UV continuum. not the Lyman continuum. I mean, we don't know. But yeah. And sorry, I forgot the question. Yeah, why? Sorry. Certainly due to the resonance scattering. You know, magnesium-2 is a resonant line, so it's scattered within the gas, and also could be absorptions on the galaxy that could create that. So yeah, to be investigated. But thank you.
All right, let's thank our speaker again. All right, next up we have Sean Johnson talking about the enrichment of the multi-phase CGM in dwarf galaxies.
All right, thank you very much. So I have to say I was a little surprised the other day when we were talking about whether or not we understand the chemical enrichment of galaxies, and people thought that we do at redshift 0 to 1, largely. And I completely believe that we can measure abundances of galaxies in this redshift range, but I do not think that we understand the chemical enrichment process. And that's because we still don't have a great handle on the exchange of enriched material between galaxies and their surrounding cosmic ecosystems, the circumgalactic and intergalactic medium. We've made a lot of progress, but we still have a long ways to go. And so today I'm going to tell you a bit about the multi-phase CGM around dwarf galaxies, which is particularly challenging to study. And so thanks to some really great introductory work by Sanj and others, I don't have to introduce absorption line techniques. The general idea is that we have foreground galaxies and background quasar sightlines. As the light passes through clouds in the CGM and IGM around these foreground galaxies, we can study them with exquisite sensitivity. And we'd like to do it for galaxies like this one, ideally. So why study the circumgalactic medium of low mass galaxies? And by low mass, I'm talking about galaxies with stellar masses of about 10 to the 8. And the reason is these are very sensitive laboratories for studying feedback. And Anna introduced the different feedback models, including blast wave, which is kind of a classic model. I'm not a simulator. And superbubbles from clustered supernovae quite nicely. But if you change between these different feedback models in a system of two dwarf galaxies, you go from these 2 points here with blast wave feedback, which are nicely on the mass metallicity relation, to these 2 points here. They shift around significantly. The metallicities change, the stellar masses change, but they are still consistent with the mass metallicity relation. So we would like to have some other perpendicular probes of galaxy evolution. And fortunately, the circumgalactic medium offers us a very nice opportunity. So this is a system of the same system of dwarf galaxies. So there's two dwarfs in here. The more massive one is at the center, and the virial radius, which is about 80 kiloparsecs at redshift 0, is visualized by this circle. The left panel is blast wave feedback, and the color bar is showing you the column density in metals at different positions from this galaxy. So with the blast wave feedback model, something like 90% of the metal yields from this dwarf are launched into the intergalactic medium on greater than megaparsec scales. With the clustered supernova feedback, this is much more confined, but still launching a substantial fraction of the metals out well beyond the virial radius, and even onto almost megaparsec scales, but not nearly so extended. And this has something to do with the resulting difference in star formation histories between these two systems. So in order to study the circumgalactic medium of dwarf galaxies like the ones that we've been talking about at this conference, we have to go lower in mass than the COST dwarfs survey, which was a fantastic study, nicely controlled with a population of star-forming and quiescent galaxies, but it's mostly centered at a few 10 to the 9. So if we want to go to these lower masses, we really need to study lower, fainter galaxies. And we have sort of two options for doing this. There's one that many at this conference love for emission line studies of gas and stars, which is to work in the local universe. And this is something where there's been significant progress for dwarf galaxies and their studies of their CGM around galaxies that many of you know the names of. This is a compilation from Yong Zhang's recent paper from 2024, which is both new data points from her own survey and also a compilation from the literature. So for example, you can see IC 1613 in these. So each of these plots shows column density in a different ion versus the impact parameter of the quasar sightline. So you can think of this like the distance at which that CGM gas is, normalized by the estimated virial radius of that dwarf galaxy. These are all less than 10 to the 9 in stellar mass, and to the best of our knowledge, these are fairly isolated, or not satellites, at least, of more massive galaxies. And the thing that is really striking, at least to me, about this plot is that you look in low ionization gas, silicon-2, almost all upper limits with non-detections. Silicon-3, you see some detections at less than about a quarter of the virial radius, and beyond that, so this is sort of the inner circumgalactic medium, and beyond that, again, non-detections with upper limits. Moving to slightly more highly ionized gas, silicon-4, mostly a couple of detections, again, within about a third of the virial radius, and then beyond that, mostly non-detections. And even in carbon-4, we have a handful of detections within about half of the virial radius, and mostly non-detections at larger distances. And as I showed in 2017, and Yong showed with much better statistics, the CGM traced by silicon-2, 3, 4, and carbon-4 represents a relatively small fraction of the metal budget of these dwarf galaxies, which is, at least to me, a surprising result, because these are low-mass systems, they have low virial temperatures, and so at least naively, I was expecting the low ions to dominate. But this presents a challenge. So either all of these metals are being ejected into intergalactic space, like some of the models suggest, or they're in ionization states that we're not tracing locally. And local studies of the CGM of dwarf galaxies present a challenge. And that's summarized by this quasar spectrum here, where I've taken the typical redshift from these local studies, and I've placed the H1 Lyman alpha line on the quasar spectrum. It is just murdered by the Milky Way damping wing and geocoronal Lyman alpha. And if you want to study higher order Lyman series lines, like say Lyman beta or highly ionized gas traced by oxygen-6, which is the most common metal line detected in the redshift less than 1 universe, we don't have any data over here. You might say, stupid observer, you picked the wrong grading settings. This is actually Hubble. So this is the effective area of COS as a function of wavelength, and below about 1150 angstroms, this drops like a rock, and that is because of the telescope. No instrument can change this. We really need to keep this in mind with habitable worlds, I think. So what can we do? We can move to what I call high redshift for the purposes of this study, which means redshifts greater than about 0.1, so relatively close. So we got very, very lucky in 2017, where one of our quasar sightlines that is in the archive at redshift 0.65, which is at the center of this image, just by happenstance, probes the CGM of 2 different dwarf galaxies at different redshifts. So this one here at 16 kiloparsecs from the quasar sightline is a 10 to the 7.9 stellar mass galaxy. And this one at redshift 0.16 is slightly more massive, probed at 21 kiloparsecs. And just for reference, these are roughly main sequence dwarf galaxies. And when you put them at even redshift 0.1, which is not high redshift, they are still a little bit fainter than 23rd magnitude in the R band. So we're pushing relatively faint already. If we go and look at the absorption as a function of velocity relative to the galaxies, we see strong H1 associated with this dwarf, seen in Lyman alpha, Lyman beta, which is actually still saturated. We see strong oxygen-6, and we see a smattering of lower ionization lines. And in the other one, we see strong H1 in Lyman alpha, Lyman beta, strong O6, and actually quite weak lower ionization lines. So we're actually starting to detect the highly ionized phase in the CGM of these dwarf galaxies. We put together a very modest statistical sample where you can see H1, silicon-2, 3, 4, carbon-4, and oxygen-6 all here, and found that the oxygen-6 phase is by far the most sort of cosmically abundant, and if you make some plausible ionization corrections, it could account for at least about 40% of the metal budget of these dwarf galaxies. So now we can actually do a lot better with something called the Cosmic Ultraviolet Baryon Survey, which combines, there's a large team, I can't introduce everyone, which combines 169 orbits of far UV spectroscopy with COS, with a dedicated ground-based galaxy survey, including MUSE integral field spectroscopy and wide field follow-up to characterize environments. And this is a major initiative representing lots of Hubble time and also 40 nights on Magellan. And a graduate student, Nishant Mishra, at the University of Michigan, is working on using this to improve the statistics for our studies of the CGM of dwarf galaxies. So for example, this is a stellar mass of 10 to the 7-ish galaxy at redshift 0.7. This little bit of fuzz right there, we can only detect this because of MUSE. It is a little bit fainter than 26th magnitude, but we can detect oxygen-3 emission lines and get its redshift nice and cleanly. And what Nishant found is that H1 is quite common, consistent with before. Low ionization state gas traced by carbon-2, quite rare. Carbon-3, a little bit more common, but still pretty rare. And now we have oxygen-6, which shows up in roughly half of the sight lines probed at less than the virial radius, and we see occasionally just beyond the virial radius. And so this is about a 50%, what we call covering factor. So Nishant put together a mass budget and found that if you take ionization corrections, you get mass estimates that agree with what we did back in 2017. And now if we assume a fiducial metallicity, we're starting to talk about a substantial fraction of the baryonic budget of these dwarf galaxies in the oxygen-6 bearing phase. Interestingly, when we look at the kinematics, so this is the velocity of the absorbers relative to the galaxies as a function of projected distance normalized by the virial radius, where the error bars are not error bars, they're the absorber widths. We found that only 20% of these dwarf galaxies show evidence of unbound metal absorption. So these dwarfs are actually quite good at hanging on to their metals. They're ejecting it out of the ISM nicely, but it's sort of hanging around in their local cosmic environments. So now I'm going to show some preliminary results that are new as of basically last night. So we can start to estimate metallicities for these systems using the different ionic column densities and some modeling. This is a metallicity of about minus 0.5 in log relative to solar. Another system where we have something magical happening at redshift 0.4, we have O2, 3, and 4 all shifting into the far UV spectrum. So we can get an O on H of minus 0.5, so not super low, not super high. And we also have carbon and nitrogen lines, so we can actually start to study the relative abundances. And carbon and nitrogen are underabundant relative to solar in these systems. So you saw Will talk about what else we can do with this data in terms of the giant quasar nebulae, and I will leave you with my conclusions. Thanks.
Questions for Sean? I'm going to count to 5. Raise your hands.
So the ionized oxygen-6, is it basically ionized gas which has fallen out, or is it like some kind of photoionization happening in situ outside the CGM kind of?
Yeah, so I don't have direct constraints on this from line ratios yet, but I think that this is basically just photoionization. The dwarf galaxy CGM is low in density, and so the metagalactic UV background just ionizes it.
More questions? Yep.
Hey, Sean, I'm surprised at the relatively high metallicities that you're inferring here.
Yep.
I'm curious, A, how large are those compared to the ISM metallicities of those galaxies? And then B, if it is fairly metal enriched, do you have any guesses as to what mechanism is preventing that relatively enriched gas from cooling and reaccreting onto the galaxy? And then we have an issue of like bringing in a lot of new metals instead of keeping the metallicities low in these dwarf galaxies.
Yeah, so these are slightly higher than the ISM, although the ISM metallicities for some of these systems are quite rough because some of them are very low signal to noise spectra. So yeah, they're on the high side, but they're not super high. So I don't actually expect it to be cooling super, super fast. The metal line cooling really starts to kick in at slightly higher metallicities when you're at this density and photoionized by the UV background.
All right, time for one more question. Oh,
So I'm hi. So I'm a little bit surprised with the 20% unbound metal components. So, how much projection effect do you expect to be there?
Yeah, so we decided to adopt the same definitions as Gwen Rudy did in her 2019 paper. So this, when I say unbound, I mean it is, unless we have the mass of these systems very wrong, it is definitely unbound. So you could increase this to maybe 30% if you account for projection effects.
all right, I saw one more question over here. If Ramona, you want to come set up, and we can do this last question.
Just wanted to hear a bit more about the O2 emitting nebulas, but maybe it's a bit late for that. So
They come from everything: accretion, stripping, and outflows. That's what I'll say for now.
thank you.
All right, let's thank Sean again.
Spoilers.
All right, so next up we have Ramona Augustin from Potsdam talking about the stellar masses of gas-rich absorbing galaxies.
All right, can you all hear me? Great. Great, thank you very much for giving me the opportunity to present my work here today. I'm Ramona Augustin, I'm a postdoc at AIP in Potsdam, and today I will talk a little bit about the stellar masses of galaxies that are associated with high H1 column density absorbers. So the context here is that we're trying to understand the circumgalactic medium, and particularly how galaxies relate to the gas that sits around them. So we've heard this already today, but we know that all the fuel for the galaxy to grow and form stars must travel through the CGM. So we maybe don't really know, but we expect very strongly that the evolution of the CGM is also closely connected to the evolution of the central galaxy, and therefore we want to understand what's the connection between the two. To draw this connection, first of all, we need to observe the CGM. And ideally, we would like to look at it in emission, but as you all know, this gas is extremely diffuse, therefore very faint. And to do this for the full halo is quite challenging, even with the strongest emission lines. So what we're doing in this work is to use the more, let's say, conventional approach to look at observers towards background quasars. But of course, if you look at these observers, we also have to find the galaxy that's associated with that. And this search for host galaxies has been facilitated immensely over the past years by the use of IFU data, where we can take an image of the quasar field, and we get a spectrum for each pixel in this image. And therefore, we can get spectra for every object in the field and determine its redshift so that we can do the matching of the galaxies with the observers. And what have we learned in the past? So typically, we like to look at the strongest H1 observers because we think that they are closely connected to the central galaxy disks. And we've learned already that the metallicity, for example, that's probed in the halos in these DLAs follows the expectations from the mass metallicity relation for galaxies once we correct for a flat metallicity gradient into the halo. But more curiously, maybe, recently we found that there is an apparent anticorrelation between the probed H1 column density in the halo and the stellar mass of the counterpart. And this is all the data that we had available in 2018. So today we're trying to revisit this parameter space and see if this anticorrelation holds. The data that we want to put into this plot comes from the Muse-ALMA Halo survey. This is a survey that aims to study the galactic baryon cycle. And since we know that the gas in the galaxies and around them is multi-phase, we also need multi-wavelength observations to capture the different phases in the gas. So let me walk you through that real quick. So we have, as is mentioned, absorption spectra. So these are UV spectra going through the halo. Full